Hello all and welcome to Physics with Pranav. If you're new here, I'm Pranav and I really love physics and I also really enjoy teaching people, I have helped many students who study the CAIE curriculum to score excellent grades in their IGCSE and A-level physics examinations. I'm also a CAIE student myself and was a world topper in IGCSE science in 2013. My hope with this channel is to provide you with the preparation methods that help me and the students I taught achieve success in their examinations. I'm going to use a consistent approach across my videos, and it's a fairly straightforward approach. The first step of my approach is to prioritize. There's going to be loads of topics and loads of chapters, but the best thing to do is to understand what are the most tested topics within each chapter and devote most of your time to be preparing for those particular topics. So the first step is prioritization. The second step is once we have identified the key topics, it's to be sure that we have solid foundations, right? So this is about understanding those concepts and being confident in applying them. And the third step is to actually apply these concepts by working out past papers, because practice makes perfect. So I will be releasing 2 videos for each chapter in the CAIE curriculum. The first video will be looking at the most commonly tested topics, and it will be looking at the concepts behind these topics. And then I'll be releasing another video where I walk you through past papers that I've done so that you can put these concepts into practice. So I'll be starting off with chapter 2 in this video, which is motion in the CAIE IGCSE curriculum. So without further ado, let's take a look at the key tested concepts in motion, as well as what you need to know about these. So firstly, there are 2 essential things in this topic. The first is calculation-based, and the second is description-based. And within calculation-based questions, there are 2 types of calculation-based questions. So you've got formulae-based calculation questions and graphical style calculation questions. So the formulae-based calculation questions are essentially scenarios where you use formula, which we'll be looking at, to be able to calculate the quantities of distance, displacement, speed, velocity, and acceleration. Then you've got graphical style questions where you would be expected to calculate these exact same quantities, but by looking at a graph and being able to calculate things from a graph. You might also be expected to plot things on a graph based on the description of a scenario for how these quantities change. The third thing, or rather the non-calculation bit, but the second major topic being description-based questions, will look at your ability to describe how the quantities of distance, displacement, time, speed, velocity, and acceleration change in certain situations. And a commonly tested situation here would include freefall, which we will explore. So you can see that I have looked at questions from 2020 to 2022. I've looked at both paper 2 and paper 4, paper 2 being the multiple choice paper and paper 4 being the theory paper. I've looked at all 3 variants, so variants 2.1, 2.2, 2.3, as well as 4.1, 4.2, 4.3, and I've looked at papers from across the year. So I've started off at Feb-March, which is commonly tested in South Asia, and also looked at summer, which is May, June, and winter, which is October, November. So that we get the full breadth and the full, range of papers that are, commonly tested around the world. I have to say that I've included 2020 to 2022 simply because these is very recent, and the questions that or the concepts that have appeared in these papers are very much likely to reappear in papers in the future. I do have to say though that obviously it's very important that you review the full curriculum, all the topics and all the concepts with them are comfortable about it, because we never know what a future paper can test. There might be a question from a topic that's not commonly tested that can show up, and you don't want to be caught out. So that is a general recommendation. But obviously, the concepts included here within the topic of motion are the most commonly tested ones. So if you were to prioritize your preparation, I would start by looking at these concepts. So I have to say, within these concepts itself, the graph cell questions are the most common in both paper 2 and paper 4, with the second most common type of question in paper 2 being the formulae-based calculations, whereas in paper 4, I think the second most common type of question revolves around describing scenarios where these different quantities change. Okay, so without further ado, if we look at the formula relationships, so the way I like to do this is I like to use these triangles essentially. So the way I would read this triangle is you've got a quantity on the top and two quantities in the bottom. The two quantities in the bottom are multiplied together to be able to obtain the quantity on the top, right? So when we look at kinematics, as this topic is generally referred to in physics, or motion, as the topic name is, you will find there are two triangles involved. So the first is your displacement, velocity, time triangle, and the second is your velocity, acceleration, and time triangle. Yeah, I just have to say that displacement can be substituted for distance, and velocity can be substituted for speed. So essentially, displacement is the vector of distance, and velocity is the vector of speed. So we will be exploring vectors a little bit further in a moment, but the key thing to understand is that vectors tend to have a magnitude or a value and a direction, whereas scalars, which are quantities like speed and distance, tend to only have a magnitude. So what I mean by that is a velocity is a vector because you would say something is traveling at 100 kilometers per hour towards the north, right? Whereas speed would just say that an object is traveling at 100 kilometers per hour. It would not mention the direction in which it's traveling. It could travel north, south, east, west, or in any of the combinations of those directions as well. So that's the key thing to keep in mind. But we will look at vector additions a little bit later. But the key thing to remember is there are two triangles, displacement, velocity, time, or distance, speed, time, and then velocity, acceleration, time, or speed, acceleration, time. So that's the thing to keep in mind. And as I mentioned, if you want to get the quantity at the top of these triangles, you have to multiply the two quantities at the bottom of these triangles. So displacement will be a product of velocity and time. Velocity will be a product of acceleration and time. Equally, if you want to get one of the quantities in the bottom, you always have to take the quantity at the top and divide it by the other quantity in the bottom. So if I wanted to find, say, the velocity and I have displacement and time, I would divide displacement by time to be able to get my velocity. Likewise, if I wanted to get, say, time and I've been given velocity and acceleration, I would have to divide velocity by acceleration to be able to get time. So the key thing to remember is you can obtain the quantity on the top. If you know the two quantities in the bottom, you just need to multiply them out. And you can obtain the quantity in the bottom. If you know the quantity at the top and the other quantity at the bottom, you just have to divide the quantity at the top by the other quantity at the bottom, and then you would be able to get the other quantity at the bottom. So that is an easy way to remember the formulas essentially in this chapter. The next thing that we'll look at is the most commonly tested concept, which is graphical relationships. So I've got here a displacement time graph, right? So in a graph, you've got a y-axis, that's your vertical axis, and then you've got an x-axis, which is your horizontal axis. So in all of these motion-related graphs, time is always on the x-axis or on the horizontal axis, and then one of displacement, velocity, or acceleration will be in your y-axis. Again, this can be a distance time chart as well, but I am just going to be using the vector equivalent throughout this chapter. So before we dive deeper, the key thing to note is that we'll be discussing the concepts of gradient and area when we look at each of these graphs. So what do I mean by gradient? Gradient is essentially the slope, right? So you can see here, if you call this region 1, you can see that in region 1, this line is sloping upwards. You can see here region 2, so that is a flat line. And you can see in region 3 that this line is sloping downwards. Now, gradient essentially tells you how slopey the line is, or how much the line is sloping, right? The mathematical way of describing it is to find how much the line is rising by how much it is running. Or in other words, what is the change in y values for an equivalent change in x values, right? That is what we're trying to understand. So, it would be a change in y values between this point here and that point there, and the change in x values between this point here, so essentially this x value here and this x value there. That will tell you how slopey this line is in region 1. right? So in this particular graph, the y values are displacement values and the x values are time values. So essentially what we're saying is I want to find the change in displacement between the point here and the point there. And I want to find the amount of time it took to be able to get from this point to that point, or the time here minus the time there. So once I divide these two together, I will get velocity, because displacement by time is velocity. If we go back here, we know displacement divided by time gives us velocity. So the gradient of a displacement time graph is its velocity. We will see what the implication for the different gradients are. Like, what does it mean if the gradient is rising? What does it mean if the gradient is flat? What does it mean if the gradient is falling for a displacement time graph? But we will get to that in a moment's time. So that is what the gradient of this graph is. The next thing we'll be looking at is the area under the curve, or the area under the graph, right? So the way I'm looking at this, you can either look at it as two triangles in regions 1 and 3, and then a rectangle in region 2, or you can look at the whole thing as a trapezium. But the key thing is the area is going to be some form of the product between the y values and the x values. And what do I mean? So if I look at the regions 1 and 3, and if I wanted to find the areas, I'll have to do half base into height. So that is the area of a triangle. So half base times height. So the height here will be given by displacement, and the base here will be given by time, right? The same applies here as well. The height is given by displacement, the base is given by time. If I looked at the rectangular area in the middle, I have a rectangle, so the area would be the length multiplied by the breadth. The length is a unit of time, the breadth is a unit of displacement. So again, it's going to be a form of displacement into time. So essentially, and if you look at a trapezium as well, the same tends to apply, where you would have some form of the y-axis values multiplied by the x-axis values. So if we do that, we will see that the area we get is a displacement multiplied by time. But no such quantity exists. If you go back here, you know, these are the only two triangles we have, and obviously there's scalar equivalence of it. By scalar, I mean displacement is replaced with distance and velocity with speed. And, you know, there is no triangle where displacement is at the bottom and it's being multiplied by time. You know, in the only two triangles we have displacement is at the top. So displacement is not multiplied by time to give you another quantity. Rather, if you want to get to displacement, you'd have to multiply other quantities together, right? So that means displacement times time doesn't really amount to anything, so no such quantity exists. So the key takeaway from this graph is that the gradient of a displacement time graph is its velocity, and the area under the curve for a displacement time graph doesn't mean anything. So that's the key thing to take away from this. Next, we come on to the velocity time graph. This is the most common type of graph you will come across in your papers. So here you've got velocity in the y-axis or the vertical axis, and you've got time in your horizontal axis, as always. Again, if you look at the gradient, which is the slope or the change in the y values by the change in the x values, here the y values are velocity values, the x values are time values. We know that velocity divided by time is acceleration. So if we go back here, we can see velocity divided by time is acceleration. So the gradient of a velocity time graph is acceleration. The same applies for a speed time graph. The gradient of a speed time graph will be change in speed by change in time, and that's going to be equal to the acceleration as well. Again, as with the displacement time graph, we'll be looking at what the different gradients mean. You know, what does a rising gradient mean? What does a flat gradient mean? What does a dropping gradient mean? We will have a look at that in some time. But the key thing to remember is the gradient equals the acceleration. If you look at the area under the graph, as we already discussed, we've said that the area is going to be some product or some form of the product of the y values, which are the velocity values, and the x values, which are the time values. And we know that velocity multiplied by time is essentially displacement. So velocity multiplied by time is displacement. If you had speed instead, speed multiplied by time would be distance, right? So the area under the curve for a velocity time graph is the displacement, and the gradient of a velocity time graph is your acceleration. Moving on, the third type of graph is the acceleration time graph. You typically never see this graph in IGCSE exams, but I've just included it for completeness here. Again, the gradient would be the change in the y values by the x values. Here, the y values would be acceleration values. The x values would be time values. And if you divide this, you don't really get a quantity. It just tells you what the rate of change of acceleration is, or how the acceleration is changing. And again, if we go back and look at our triangles here, we can see that the acceleration is not really divided by anything to give another quantity. Usually the acceleration is multiplied by time to give velocity, but in the triangles that we have, there is no triangle where the acceleration is at the top of the triangle, where something else would have to be acceleration would have to be divided by something to be able to get another quantity. You don't really find that. So that is why the quantity that you get is more of just a rate of change, really, of the acceleration. But if you look at the area under the curve, we've said the area is a product in some form of the y values and the x values. So acceleration multiplied by time is essentially velocity, and this is validated by our table, by our triangle here. So acceleration multiplied by time gives you a velocity. So that is a quantity that exists. So for an acceleration time graph, the area under the curve is the velocity, and the gradient of the curve is the rate of change of acceleration. But again, no such quantity formally exists. So I did mention that we're going to be looking at gradients in a little bit more depth. So, but before we do that, I just want to be able to explain a few concepts for some of the terms that I mentioned. And in fact, even before that, I just want to reiterate that the gradient of a displacement time graph is the velocity, because gradient is the slope, and the slope is the change in the y values. For the x values, we know the y values in the displacement time graph are displacement values, the x values are time values, and displacement divided by time is the velocity. So with that out of the way, I mentioned terms like positive linear, negative linear, no gradient. So this is this is 3 of 7 graphs that we will be looking at for displacement time graphs. And here we've got positive nonlinear, negative nonlinear, and I've got terms such as flatlining, rising, and dropping written underneath those. So what do I mean by all of these things? So the first is, if we try to understand what positive means. So when I use the term positive in a graph, I am essentially mentioning a scenario where the value in the y-axis is increasing. You know, as you go from left to right, you're going from the bottom left to the top right. So the value in the x-axis is increasing. So that's why it's positive. The negative is going to be the opposite scenario, where if you go from left to right, you will find that the value in the y-axis is decreasing or becoming more negative, right? Or becoming smaller. So essentially it goes from the top left to the bottom right. So that's what I mean by positive and negative. And that applies whether or not we're looking at lines or we're looking at curves, as we see here. So we can see, again, positive curves start at the bottom left and go to the top right, whereas negative curves start at the top left and go to the bottom right. So that's what I mean by positive and negative. The next thing we want to look at is the term linear and the term nonlinear. So linear essentially means, linear refers to lines, and what I mean by linear is the gradient is constant. So we know the gradient is a change in the y values by the change in the x values, or it's essentially the slope. And we can see that for the straight line, it's a constant slope, yeah, all the way. It doesn't matter where you find the slope, but at each of these points, the slope is the same. The same applies for the negative linear, where again, you've got a straight line. It's just pointing sort of in the opposite direction, but it's a straight line nevertheless. So the slope remains constant. If you look at a curve is non-linear because, you know, at different points in the curve, the slope changes. So initially, it's quite steep, this curve, and then it gradually flattens out. Whereas if you look at this curve, for example, initially it's quite flat, and then after that it becomes, you know, more and more steeper, so it's almost vertical at that point. The same applies to these other two graphs, where the curves are in the opposite direction to the curves in these two graphs, but essentially they are curves nevertheless. They are not lines, so they are all non-linear. So that's what we mean by linear and non-linear. And we will, you know, when we explore the curves, I will explain what flatlining, rising, and dropping mean. But if I start off first with the linear curves, you can see that, the linear graphs rather, you can see that here is a straight line. It just goes up. So we know that the gradient of a displacement time graph is the velocity. In this case, the displacement is increasing. So we know, and we have a constant gradient because it's linear. So we know that we've got a constant velocity or a constant speed if it's a distance time graph. But I've mentioned that it's a constant speed moving away from the source. So what do I mean by that? So essentially, displacement is a vector quantity, right? So if we assume that your house is the source, then what we're saying here is that as the displacement increases, the object is moving further away from your house, or rather, the distance from your house of the object is increasing. Okay? If I look at the negative linear scenario, again, we know that because it's linear, you have a constant velocity. We know that because it's the gradient of displacement time is the velocity. But the fact that it's negative, or the fact that the displacement is essentially decreasing in the graph, means it's like the object is coming back towards your house, which is the source. So in the first scenario, it's like you start your car and you're going away, traveling at a constant speed or a constant velocity away from your house, and your displacement from your house is increasing. Whereas in the second scenario, again, you've got your car, you're traveling at a constant velocity, but you're traveling back towards your house, which means the displacement or the distance from your house to your car is decreasing till it eventually becomes a zero, right? So that is what the positive and negative stand for in a displacement time graph. The third scenario that I have here is a no gradient graph. So in a no gradient graph, if you think about this graph, you've got a value of displacement, and this value of displacement stays the same as time ticks along, because remember, time is always in the x or the horizontal axis. So what does that mean? So it's like you've traveled a certain distance away from your house in your car, and then after that, your distance has not changed. Your distance stays the same irrespective of time ticking away. So this could be a scenario where you traveled a certain distance and you're stuck in traffic, or you probably reached your destination at the time the graph started capturing the information, and then you parked in a parking lot somewhere, and the displacement remains the same because your distance from your house is the same over time, but you're not increasing or decreasing the distance from your house. So essentially, this is a classic scenario of an object at rest, or what we also call a stationary object. So moving on to the curves, I did mention that I will dive a little bit deeper into what I mean by flatlining, rising, and dropping. But we do understand the concept of positive and the concept of non-linear and negative and non-linear. So positive means essentially displacement is increasing from the source, or the object is moving away from the source. In the case of you in your car and your house, you're moving away from your house. Negative just means you're coming back because your distance between your car and your house is decreasing because you're returning. And non-linear, well, non-linear essentially means that the gradient keeps changing. And if the gradient in a displacement time graph keeps changing, because the gradient is the velocity term, that means that the velocity is changing. And if the velocity keeps changing, that means the object is either accelerating or it's decelerating. So it's accelerating if its speed is increasing, and it's decelerating if its speed is decreasing. Okay, so that's basically what a nonlinear graph shows. Essentially, a nonlinear graph for a displacement time graph is one where the object is not traveling at a constant velocity, but it is either accelerating or decelerating. So flatlining means that as you start from the left and go to the right, the curve becomes flatter and flatter till it becomes a line. It almost goes to becoming this no gradient line that you have here. So if you look at your first and third graph here, you can see that here the line starts to flatten out. You can see that here, again, the line starts to flatten out. So that is what we mean by flatlining. And we know that a flat line means that the object has become stationary in a displacement time graph. Yeah. So if you look at these two scenarios here, if you look at the first and third scenarios, in the first scenario, you've got an object that is moving away from the source because you've got a positive curve. It's nonlinear, which means it's either accelerating or decelerating. But you know that because it reaches a rest, a state of rest towards the end, it can't be accelerating. It has a certain velocity, and then its velocity goes to 0, which means it's clearly slowing down. So it's a decelerating body. So that's what essentially this graph is describing. It's describing an object that is moving away from the house, and it's doing so slower and slower and slower. It's decelerating till it ends up stationary. In this other scenario, you've got something similar where you have an object that's decelerating because, again, it ends up at rest, but initially it has some velocity. But it's negative nonlinear, which means it's essentially moving towards the source. In this case, your car is moving closer and closer to your house, and maybe at the end you park in your parking lot, and your car stops. So that's a classic example of that. And maybe the positive nonlinear is a classic example of, say, you take your car and you want to drive it to a shop, and then you reach the shop, and then you basically park it outside the shop. So that's essentially what's happening, and you don't travel at a constant velocity throughout. So that's essentially how I would describe these two graphs using a real life scenario. If I look at the second and the fourth graphs, in the second graph, you got, again, positive nonlinear, which means, it's an object, it's moving away from the source, and it's either accelerating or decelerating. We don't know just yet what it's doing, but you can see that the slope keeps increasing as you move away from the source. So the fact that the slope keeps increasing means that the velocity keeps increasing, because the slope equals the velocity in the displacement time graph. And an increasing velocity is akin to acceleration. So what you have here is a body that's moving away from the source and is doing so faster and faster. So it's accelerating. So it's like you leaving your house with a car, and then you press on the gas once you leave your house, and say you join like a motorway, and you're just going faster and faster. Motorway, by the term, is the term that we use in the UK for the highway. So yeah, please don't get confused if I use motorway and highway interchangeably. In the last scenario, you've got negative nonlinear dropping. So what I mean by this is you've got an object that is traveling at a certain velocity. You can see that the gradients are getting sharper and sharper, albeit in the opposite direction, or rather they're getting more and more negative, which means your velocity is still increasing in value, yeah, but you are moving closer to the source. So essentially what we have in this particular scenario is we've got an object that starts off from somewhere, is moving towards the source, and it's accelerating towards the source, right? So that's essentially what is happening here. So this could be an example of where you're returning from the shop and you just want to get back home. So, you're accelerating back towards your house. So that is how I would describe these scenarios for a displacement time graph using the different gradients. If you move on to velocity time graphs, the most common type of graph, in a velocity time graph, again, we know what the terms positive, linear, non-linear, flatlining, dropping, and rising mean. So positive, essentially, for a velocity time graph means that there is an acceleration. So why do I say that? So in a velocity time graph, the y-axis is velocity, the x-axis is time. So we've got a scenario where the y values are increasing, which means the velocity is increasing. And when the velocity is increasing, you've got an object that's accelerating. If it's linear, that means the gradient remains constant. We know that the gradient of a velocity time graph is the acceleration. So basically, that means we've got a constant acceleration. If you have a negative linear graph, you've got constant deceleration. That's because, again, the gradient of the graph suggests that the object is accelerating or decelerating in a velocity time or a speed time graph. And the fact that it's negative means that the value of the velocity keeps decreasing. And the fact that the value of the velocity keeps decreasing means it's slowing down, which means it's decelerating. So negative linear velocity time graph shows a decelerating object, and the rate of deceleration is constant. And then finally, you've got a no gradient graph. So what I mean by this is, again, if you think about it, your y-axis values are velocity values, your x-axis values are time values. And what we're saying is as time ticks on, you've got a constant velocity, a constant value of velocity, which means the object is neither accelerating or decelerating. It's just moving at a constant speed. Yeah. So the first scenario could be an object that's, if you just start your car off and you're trying to get, up a few gears, you press on the gas a bit, you got a bit of constant acceleration, and you're moving away, right? In the second scenario, maybe you're traveling at a certain speed and you see the traffic lights are going red and you want to slow down, so you press on the brakes and then you do it gently, and then you got a bit of constant deceleration. And the final scenario, talking about constant velocity, so this could be you're not near a signal, you're not starting or stopping anywhere. You're just traveling at a constant speed. Maybe you're traveling at the speed limit of the road that you're on. So that is the third scenario. And now if you look at the curves of the nonlinear cases, positive nonlinear. So positive means, again, the object is accelerating, but nonlinear means that the rate of change of acceleration is not constant. And then we know that flatlining, so when we look at a velocity time graph, a flat line or a no gradient line means that we've got constant velocity. So what is happening in this scenario is that the rate of acceleration is slowing and the object is reaching a constant speed. So this could be a scenario where, it's a bit of initial acceleration and then you slow down as you move away from your house in your car, and then you join, a road and you reach the speed limit of that road. So, you hit a constant velocity there. The second scenario is basically a positive nonlinear rising scenario, where positive nonlinear means, in the case of velocity time graph, you got an acceleration. The rate of acceleration is not constant because it's nonlinear, and the fact that it's rising means that the gradients keep increasing or the slopes keep increasing, and that means that you've got an increasing acceleration. So this is just someone who's in their car, who's got their foot on the accelerator or the gas, and they're just accelerating. The speed is like ever increasing. So this could be a car that's just joined the motorway that just wants to, catch up to speed to 70 miles an hour or 60 miles an hour, depending on the motorway you're traveling in. We've got the third scenario, which is negative nonlinear, flatlining. So negative means the object is decelerating. Nonlinear means the rate of deceleration is not constant. Flatlining means it's eventually reaching a constant velocity. So here you got an object which is decelerating, whose rate of deceleration is slowing, and it eventually ends up having a constant speed. And then the final scenario, you've got negative nonlinear dropping. So again, negative equals deceleration, nonlinear equals a non-constant rate of deceleration, and then you've got dropping, which in this particular scenario means, again, the gradients keep increasing, but the object is decelerating, which means slowing down sharply. So this could be a scenario where someone's traveling really fast and they see the signals change and they're not very far off and they jam, the brakes. So you got like a sharp stop, so you got an increasing rate of deceleration. So that is how I would describe this scenario here. So hopefully that made sense. I've captured this in a table here. I've also included some of these scenarios for an acceleration time graph. Again, these graphs, you don't really get tested on these graphs in your GCSEs. But again, for completeness, it's still good to know what the different scenarios mean. And I just want to say as well, I will pause here for a second. So you can either make a note of this or you can screenshot the video at this point. So you've got this for reference. Assuming you've done this, I am now going to move forwards to the next concept, which is calculating resultant velocity. So first thing to keep in mind, and touching back on something I mentioned earlier, is that velocity is a vector, which means it's got a value or a magnitude and a direction. So here we've got an object which has a mass m, and it has two forces acting on it, say, which result in different velocities. So it's got two essentially things acting on it, which result in two velocities in two different directions. So the first velocity, we can think of it as acting on a horizontal scale, and the second velocity is acting on a vertical scale. So we know that the horizontal axis is the x-axis. So that's why the velocity acting in the horizontal axis, I've called it the component of the velocity acting in the horizontal axis, I've called it Vx. Yeah, and then the component of the velocity acting in the vertical axis, because the vertical axis is the y-axis, I've called it Vy, right? You can see that both these vectors now have the same magnitude or value, so they both, have a value of 5 meters per second. But you can see that Vy, which is acting downwards, has a value of minus 5 meters per second. I mean, clearly you can't have negative velocity, or rather negative speed. So what do I mean by that? So essentially what we're saying here is we are trying to assign a value and a direction, and we are saying, according to convention, that certain directions are positive and certain directions are negative. So what I mean by this is, usually the convention goes that if you're moving to your right on the horizontal axis and if you're moving towards the top, the general convention goes that those values are positive values. Equally, if you're moving to the left in the horizontal axis and if you're moving downwards in the vertical axis, then you've got negative values. So essentially, we're just trying to show that, yes, both of these vectors have the same values, but because one is in the positive direction, the other is in the negative direction, we have given them this, we've stuck to the convention, and we're calling this 5 meters per second, whereas we're calling this minus 5 meters per second. So how do we add vectors together, right? So the way of adding vectors together is fairly straightforward. What we've got to do is we've got to start with one of the vectors. So you can see that each vector has a head and a tail. So the head is the arrowhead, and the other side is the tail. So you take the first vector, and then you just place it, and then you take the second vector, and then it's going to be head to toe. So the head of the first vector is where you place the tail of the second vector, and then after that you've got the second vector placed facing the direction that it's facing. Now if you want to find the resultant vector, which I've shown in blue here and which I've just called v, the resultant velocity in this case, all you've got to do is you've got to start the tail of the resultant vector arrow where you have the tail of the first component vector. So the component vectors here are your Vy and your Vx. They're the components of the resultant, which is the V. So you want to start the tail of V at the tail of your first vector, and then you want to have the head of your resultant at the head of your second vector. So this makes sense if you think about it, right? If you look at this object here, you've got a force that's acting towards the right, you've got a force that's acting down. So you would expect the resulting velocity of the body to be sort of downwards to the right, right? It's going to be something like this, the direction in which my mouse is pointing. And that's what the resultant velocity is showing. So that means you've oriented your component vectors correctly. If you hadn't oriented them correctly, you'd get sort of silly results, like maybe it's pointing downward left, when that is clearly not the case, because how would you get downward left if you got one velocity that's acting downwards, the other that's acting to the right, and they're at right angles at each other? So that wouldn't really be possible, right? So that makes sense. That's a quick and easy check you can do. Like, you can just use your intuition to think of what direction is the vector going to be pointing up. And the next thing is, right, once you've done this, how do you actually calculate the value of the resultant? You've got the values of the components. How do you calculate the value of the resultant? So there's two ways in which you can do this. The first method is called the scale method. And this is the easier method if you're not comfortable with Pythagoras, you're not comfortable with trigonometry, or you have a non-right angle triangle. So how do you do the scale method? So you set a scale like you have on a map, right? So you say that 1 centimeter represents 1 meters per second, say for example. So then Vx would be 5 centimeters long. So you draw an arrow that's 5 centimeters long. Usually in your question papers, you have like quite a bit of area given to you to be able to draw your vectors and be able to do the scale drawings and show the results. So you got Vx, and if you take a scale of 1 centimeter equals 1 meter per second, you would have a 5 centimeter arrow that's pointing towards the right, and then Vy would be a 5 centimeter arrow that's pointing towards the bottom, and then you would add the arrows up like you would in this drawing, and then you would join them together, with another arrow that you draw using a ruler, and then if you wanted to measure, essentially, if you wanted to know how big the resultant velocity is, all you need to do is really measure the length of your resultant velocity arrow using a ruler, and then you just need to apply the scale. So in this case, the scale is every centimeter is a meter per second. So if I were to measure this, I haven't done this to scale, but if I were to measure this, I would get a value of around 7.1 meters per second. So essentially the length of the line would be 7 centimeters. Yeah. So this is a good method if you don't feel comfortable using Pythagoras, which we'll get to in a second, or if you don't feel comfortable, if you're not comfortable with your trigonometry for angles, or if you have two vectors that are not perpendicular to each other. So in this example, you can see that the angle between the two vectors is 90 degrees, but that doesn't have to be the case. And in such a scenario, especially if you're not comfortable with trigonometry, the best thing to do is just use scale drawings, because as long as your scale is correct and consistent, you will always get the right answer. I think before I leave this method as well, I do want to add that you will be asked to calculate an angle as well. So they could ask you the angle relative to the vertical direction or the angle relative to the horizontal direction. Again, what they mean is what is the angle that the resultant velocity makes with the vertical vector, or what is the angle that the resultant vector makes with the horizontal component of the vector. So that is what you need to be able to calculate. And if you use a scale drawing, the easiest way to do that is to carry a protractor, place the center of the protractor where the lines meet, or the arrow arrows meet, and then all you've got to do is measure the angle. This is something that you would have done in geometry in class in earlier years. So I'm not going to go into too much detail there, but that's an easy way of being able to obtain the angles. So if you have a right angle triangle, though, I find the easier thing to do is to just use Pythagoras. So Pythagoras says that the square of the longest side of a right angle triangle, which is the hypotenuse, is equal to the sum of the square of the other two sides. So in this case, the longest side is the resultant velocity side, always is. That's going to be v squared. And then it's going to be the sum of the square of the other two sides, which is the sum of the square of the two component vectors, which is vx squared plus vy squared. Again, here I do interchangeably use vector and velocity, but velocity is a vector, which is why I'm saying that. But equally, as we will see in the next topic of forces, you could have arrows that represent forces, which are also vectors, and you would be adding them up in a very similar manner. So yeah, this is the Pythagoras formula, and if you just rearrange and make v the subject of the formula, you will be able to get its value to be 7.1 meters per second. So just plug in 5 meters per second for vx and vy, square them up, add them together, and then square root them to be able to get the value of v, and it should give you around 7.1 meters per second. So this is a quick and easy method to use if you are comfortable with Pythagoras. You can also be able to find the angles using either trigonometry, or you can still use the protractor, as I mentioned earlier. But if you were to use trigonometry, then usually the angle with the vertical vector, you can always find that either by using sine theta or cosine theta, which is usually sine is the opposite by the hypotenuse, cosine is the adjacent by the hypotenuse, and you can do the same for the horizontal angle between the resultant vector and the horizontal vector. But again, the easiest thing might be just to use a protractor if you have one, and I would always advise you to carry one for your exam, just in case you get a question on resultant velocity or resultant forces, as we will see. So hopefully that made sense. And the last topic, which is related to describing scenarios, is freefall. So I've taken this screenshot from the CAIE Physics textbook. So if you look at this graph, it's a speed-time graph, and I have split the graph into two areas using the dotted line. So I've called the first area the region of free fall, and I've called the second area the region of parachute assisted fall. In the text as well, they show you where the parachute opens. And if I were to describe this, I will describe it as follows. So if we take the first part of the curve here, we can see that we have a positive, non-linear, flatlining curve in a speed time graph. So we know that positive means that there's an acceleration because the speed is increasing. We know that non-linear means that the rate of acceleration is not constant. And we know that if it's flatlining, it means that its speed is slowly, its acceleration is slowly reducing till it reaches a constant speed. Yeah, and that constant speed for a falling object is also called its terminal velocity. Yeah, so sometimes you'll be asked to mark an area of terminal velocity on a free fall graph, and you should be able to mark it, correctly. So there are two areas of terminal velocity, as we will see, but this is the first area, so it becomes a flat line there. So that's the body falling without any parachute, but it's falling at a constant speed, which is a fairly high speed. So obviously for safety purposes, you would want to reduce that speed, which is why a parachute is opened. And then you've got another curvy section of the graph. So you can see that here you've got essentially a negative, non-linear, flatlining gradient. So what do I mean? Negative means obviously in a speed time graph or a velocity time graph, that means the object is decelerating. If it's non-linear, then the rate of deceleration is changing, it's not constant. And then after that, if it's flatlining, it means that essentially it's settling into a new terminal velocity or a new constant velocity. So you've got an object here that is slowing down drastically, and then ending up at a new constant speed, and that's the new terminal velocity. So you've got two regions of terminal velocities there. That is before the parachute is opened. That is after the parachute is opened. And then in the end you have a sharp drop in speed till it becomes 0. And that's the point where the object lands. So, when, say, if you've done a bit of skydiving and then you get your parachute and eventually you touch base on the ground, your speed drops from whatever it was right before you were hovering on the ground till you actually touch down on the ground, and then you have a speed of 0. So that last bit there shows that the object has landed. So the key questions you usually get is you would be sometimes expected to describe the motion of the object. And we've said that initially the object is accelerating, but its rate of acceleration is slowing. This is because, as we'll see in the topic on forces, you've got the force of gravity acting on the object, and you've got initially minimal air resistance, but then as the object keeps falling, the air resistance tries to oppose its motion, and then after a point you have the force of gravity balancing the drag force, and at that scenario the object falls at a constant speed because there's no net force acting on it. So essentially you've got the object falling at terminal velocity or a constant velocity. And then after, when the parachute is open, there's a massive deceleration because there's a lot of drag because the parachute has a massive surface area. And then after that again, the drag force then slows down the object to a newer, slower terminal velocity before it lands. Common questions, again, as I said, would include show the areas of terminal, where the object has reached terminal velocity, and show the area where the parachute is opened, or show the region of free fall versus the region of parachute assisted fall, or be able to demarcate it as I have done here. So that's the key things that you need to know from this graph, and be able to describe accurately and clearly. So that brings us to the end of the key concepts that are tested in Chapter 2 Motion. I will be creating a video where I will walk you guys through some questions on these concepts from past papers. And yeah, I think that will show you how to apply these concepts in real life exams. So I hope you enjoyed the video. I hope you got some value out of it. And if you did, please consider liking and subscribing. And I look forward to joining you all in my next video. Thank you. Bye-bye.